Right, hello. Go ahead and do some math today. Let's pull this back up. All right. Sorry, I had that off because I was using the tablet to upload a bunch of solution documents that we'd been working on, but I completely forgot to upload to Notebowl. So those are mostly there now. Still have like 2 more, and then I'll have the one for today. Let's see. Where is my problem set? There we go. All right. So I only have a couple problems on here today. Mostly because it's, if you can do the double integrals, you can do the triple integrals. And really, for the most part, what we need to focus on is being able to solve or to set these up more than anything. Again, just sort of like before. That's gonna by far be the more interesting part. So let's go ahead and do these, and we'll do some Mathematica bits here and there. Actually, on that note, I do have a document open. Good. All right. So let's go ahead and get started. So problem 1 is just compute a triple integral, just so we can say we've done one here. 1 to 2, 0 to 2, xy squared over z dz dx dy. So actually, since this one is a pretty straightforward just computation here, why don't I go ahead and say try this one real quick, see if you think you understand what's going on here, and we'll go from there. There's like a million cords on my desk. All right. So hopefully you've had a chance to sort of get started here. Wasn't this example supposed to have an ln in it? Whatever, that's fine. Yes. Hold up. I think I messed up the bounds on z here. I think I copied that problem wrong. Because this is an integrable. I made a mistake. Yep, copied the bounds from another problem. Cool. This should have been 1 to e. I thought something was wrong there. Let me fix that in the document real quick. And pop the new one on Notebowl. So sorry about this. Well, it's a good thing there's only 4 problems today. So you go away. And okay. Now let's hope that was the only mistake that I made. I think it is, but we'll find out. Alright. Anyway, let's try this again. So we want to integrate this with respect to z. So again, we're just gonna, just like we did for partial derivatives, we're just gonna hold x and y constant. And so we get xy squared times integral of 1 over z, which is ln of z. Well, ln of absolute value of z, really. All right, that leaves us here. All right. So now that we have this, let's evaluate it. So if we plug in e, ln of e is 1. If we plug in 1, ln of 1 is 0. Okay, so that's it. That's all we have, just xy squared now. All right, so let's go ahead and integrate that. We're going to go from -2 to 2. We're integrating with respect to x, so this is 1/2 x squared y squared from 1 to 2 dy. So we get integral from -2 to 2. Got to plug in this stuff now. The first one's going to give us 2y squared. Second one is -1/2 y squared dy. All right, just plugging in 2 and 1. So maybe we'll simplify that a little bit just to make life easy. It's going to be 3/2 y squared dy. All right, and then now just finish this off. So integrate this, we get 1/2 y cubed from -2 to 2, which is going to be 8. I'll just, at this point, you can do that. Sorry, my hands are like really dry this morning. All right. Any questions about this one? Should just be a straightforward computation. All right. All good. Sorry, my stream preview keeps getting like a minute behind. So I'm trying to like leave time for lag, but it insists on not doing so. Sorry about that. All right. Let's go ahead and look at problem 2. Maybe I'll just go to the next page for problem 2, actually. So problem 2 here, we want to find the volume of the prism, which we're going to call D. It's in the first octant and bounded by the planes y equals 4 minus 2x and the plane z equals 6. Right? So, we want to get an idea of what's going on here. So, to do that, let's make a little sketch. So we're only interested in the first octant, which is where x, y, and z are all positive. So let's draw a set of axes here. Right, this is going to be x, this is going to be y, this is going to be z. And I know I'm interested in z equals 6, so let's put that up here. Right. So what is this plane y equals 4 minus 2x? All right, so what we're going to do to graph this is let's graph the line for it in the XY plane, because this plane is going to be sort of parallel to the Z axis, right? Because there's no Z in the variable. So we graph that line and then we just make a whole plane out of it, right? We did this back when we were getting like those parabolic cylinders and stuff like that, right? So here, if we're graphing the line y equals 4 minus 2x, that's going to start up here at y equals 4 and actually ends here at x equals 2. So that's where the plane hits the xy plane. And then now we just need to sort of finish this off. So what we're going to do is draw where it hits the YZ plane. And then I give it this top at z equals 6. Here, I want to also draw a little bit of the plane z equals 6. And I want to draw my line to be parallel to this x-axis. So that's probably a little too much, but I don't know, that's actually good. And then we should draw straight down to x equals 2. Right? And then now we're going to connect this. And so this whole front right here, this whole front piece, right? So hopefully you can see the prism that's here now. Maybe I'll be green. Right, so here's the back of the prism. It's where the axes meet up. All right, so we have this kind of like, triangular prism here. And we want to find the volume of this thing. All right, so this plane in the front here, this is our y equals 4 minus 2x. This plane on top is z equals 6. Right, and all the other pieces, like back here, you have y equals 0. In the back here, you have x equals 0. And on the bottom, you have z equals 0. Right, so we have, all sorts of sides of this thing. So to set this up as a triple integral, the volume, we need to pick an order of integration. Right? And here it doesn't really matter what order we use. Let's see. We call this d, so the volume is the triple integral over d of dv. Right? So let me go ahead and say now, think of an order you think we should use, and let me know what you want to try and do. Take the first order. Do any of these work? I think this works no matter what order you do it in, so yeah. So just suggest an order. Otherwise, I'll just do a random order. All right. All right, random order it is. All right, 2. So we're going to do dy first. And then after y, we'll do x. So that leaves z for last. Okay. Right, so again, the order doesn't really matter here in this particular one, because we can do it no matter what. So if we're doing the integral with respect to y first, we want to think about how this shape is going, or how these bounds work. So when we're looking at the 3D shape, x, in our perspective, the way we've drawn it, x moves from the back of the shape to the front, y moves from the left to the right, and z goes from the bottom to the top. Right? What's important to remember is that, you know, these bounds, they always start from the smaller number and go to the bigger number. So no matter what direction you have your shape oriented, it should always do that. So if we're going to do y first, in this shape, we're going to be going from this left edge to the right edge. So the left edge is y equals 0, right? Because it stops at that plane y equals 0 on the left here. And if we pick any point there and move to the right, we're going to run into this plane right here, 4 minus 2x. So the upper bound is 4 minus 2x. Okay. Now, here's the interesting part. When we've done the first integral in a triple integral, when we've set up the bounds for that, to get the rest, the important thing to remember is we want to look at the shadow of this shape on the coordinate plane that's left over. So here we integrated out the y variable first. So we want to take this shape and we want to squish it down into the xz plane. Right? So remember, this here was 2 and this was 4. So when we squish the shape down, what we get is this shape. Let's use green. We get this region right here. This is the shadow of that prism on the xz plane. Right? We're just taking that and squishing it into the xz plane. So this is just a rectangle, so the bounds are really easy. 0 to 2, 0 to 6. And yeah, that's it for setting up the integral. Let's go ahead and compute this one. So 0 to 6, 0 to 2. Let's see. Do this integral, and we're going to wind up with 4 minus 2x. It's dx dz. Right. Do this integral. This is 4x minus x squared from 0 to 2 dz. So this is the integral from 0 to 6 of going to be 8 minus 4, so 4 dz. And so this is going to be 24. Right. So that's all there really is to this one here. Right. Any questions at all about this one? Awesome. Okay, that's it for problem 2. Let's look at problem 3. Problem 3 is a little more interesting. This one's also really hard to draw by hand, so we're going to set this up in Mathematica. But in problem 3, we're looking at D is bounded by 2 paraboloids. Y equals x squared plus 3x squared, or sorry, 3z squared plus 1, and y equals 5 minus 3x squared minus z squared. All right. So we want to look at, well, what is this shape here? So these things here, since we have y on the left and x squared and y squared on the right, these paraboloids open kind of along the y-axis, right? Whichever variable's not squared is sort of what axis the paraboloids open along. So one of them is going to be going to the left or to the right. One of them is going to be going to the left. So you're going to kind of have like this almost pill-shaped thing, right? Or capsule-shaped thing. All right, so let's go ahead and graph these things. Go to Mathematica. All right. So let's see what we're dealing with here. So let's go ahead and do a contour plot. So contour plots are great because we can just type the equation. So here, y equals x squared plus 3z squared plus 1, and y equals 5 minus 3x squared minus z squared. All right. Looks like y is going to go as big as 5. So let's say, let's do minus 5 to 5 for everything. And then we can adjust from there. Let's go ahead and plot this. All right, so we're looking at a shape like this. Let's do this. Axis true, axis origin, 0, 0, 0. Let's see, what are we dealing with here? All right, a little hard to see maybe on the inside of it, but you have one parabola over there and the other one over here, and they're kind of cutting off this shape. All right, let's see if we can't, looks like we don't need anything y less than 0, so let's cut that part off. And let's see. Hopefully we can see it a little bit better now, what's going on. All right, so we want to integrate over that shape. All right, so this is a little interesting, this one. So at the very least, we can see, we can start setting up the bounds and try and figure out what we're dealing with here. So we can see the blue one is going to be on the right side of the shape, so it's the upper bound for y. And the orange one, that cuts off the left edge of the shape, which is in here. So that gives us the lower bound for y. Let's go ahead and pop back over here. So the volume of this thing, right? So triple integral over d of dv. All right. So here, our lower bound is this first one. This is our upper bound. All right, so this is dy. And then now we have a choice to make for the other two. So before we do that, though, we need to figure out, well, what is the region that we're integrating with respect to? All right. Or what is the shadow of this? In this case, in the xz plane, right? So to do that, we just need to figure out, well, where do these two things intersect at, right? What is the shape that they intersect in, right? So what we're going to do here is try and set these two things equal to each other. So take these two, set them equal. We have x squared plus 3z squared plus 1. Okay, so that's y. I'm going to plug that in here. 5 minus 3x squared minus z squared. So let's push everything to one, all the variables to the left and all the constants to the right. So that's going to give me, let's see, move this over, that's 4x squared. Move this over, that's 4z squared. Move the minus 1 over, that's 4. All right, so it looks like we actually, the intersection, at least in the xz plane, is actually just a circle of radius 1. So we're integrating over a region that looks somewhat like this. Right, this is the shadow of that region in the xz plane. All right. So now there's something neat we can do. It's kind of hard to set up at first, but let's do this. So let's finish setting up this integral up here. And let's say, I don't know, we do z and then x. So if we do z then x, then the bottom bound here is square root 1 minus x squared. The top is square root 1 minus x squared. And z goes from minus 1 to 1. Right, so that's sort of what we're dealing with here. This won't be too bad to do, to integrate by hand even. And that's because the z squareds here are going to knock out these square roots. So it won't cause that much of a problem. Right? Let's see, how are we doing on time? I think we're doing okay. Maybe we'll go ahead and do this. So let's see if I can't copy this. Nope. Right. So when we do this, since we're just integrating one, it's just going to end up as the top minus the bottom. Let's see, this minus this is going to be 4 minus 4x squared minus 4z squared. Oh, you know what? I actually completely forgot about this part. All right, that's fine though. So now we're looking at an integral like this, and this will be actually like a little hint for next week, or for Friday. Sorry, for Friday's lecture. We're integrating this thing over a disk. We can actually switch this thing to polar coordinates. If we think of x as our usual x and z as the y direction here, then this actually becomes 0 to 2 pi, 0 to 1, 4 minus r squared, 4 minus 4r squared, r dr d theta. Right? So we kind of have here like a polar coordinates with one Cartesian coordinate tacked on, if you think about it. So let's see, 0 to 2 pi. This is going to be 2r squared minus r to the 4th from 0 to 1 d theta. That's 0 to 2 pi. This is 1. That's d theta. So there's 2 pi. All right, so the volume of that shape that we graphed there is 2 pi. All right. Any questions about that one? So it's a bit of a fun one here. Really, I think the most important part of this one, again, is setting up the integral. We do have computers to compute integrals for us these days. But I figured seeing this computation wouldn't be a bad idea. Right? Any questions at all? All right. So let's go ahead and move on to the last problem here. Right. So the last problem is evaluate an integral 0 4th root of pi to 0 to z, then y to z, of 12 y squared z cubed sine of x to the 4th. This should be dx dy dz. All right. So we want to integrate this thing here. Now, as it stands, if we look at this, we can't really integrate sine of x to the 4th power. Right? There's no trick for this. There's no u sub. There's no integration by parts that's going to get us out of this. So what do we do? Well, we do the same thing we did with double integrals, which was to try and switch the order. Right? So we have to figure out, well, how do I switch the order here? And just like with double integrals, knowing what the region looks like, knowing the shape of your region is going to be necessary to do that. So let's go ahead and try and figure this out here. All right. So here, keep in mind what the bounds of an integral tell you. So here, these are equations for z. So we know that z is between 0 and the 4th root of pi. Y goes from 0 to z. And x goes from y to z. Right? So the bounds on our integral tell us these three things here. Right? So what are these? What region does this give us? Okay. So let's try and do a similar thing here to what we did before, and see where it takes us. All right. So z, x, y. All right, so let's look at the lines x equals z and x equals y. Right? The line x equals y is going to be coming out like this. All right, I'm just going to draw that line there, and we'll see what we can build up in a second here. All right, x equals z is, let's sort of draw it there. Right? And then we're cutting off here. Let's say this right here is the 4th root of pi, whatever that happens to be. So we're going to cut off there. Let's see. So this is hard to draw. Let's see. This is quite hard to draw by hand for me. So let's plot this in Mathematica. I have a hard time drawing planes. I really do. Like if it's one plane, it's fine. but if it's multiple, it's pretty challenging for me. So let's start by doing contour plot 3D. Let's just do x equals y and x equals z for the moment. And z equals pi to the 1/4. Let's toss those in. All right, let's see, pi to the 1/4. Probably only need to go from like 0 to 2 on each of those. All right, so let's see what that looks like. Oh. Let's get that in there. All right. Okay, so here we are. So here we have so this green one right here, this is z equals 4th root of pi. This blue one, this is x equals z, and the orange one is x equals y. So we're kind of looking at this sort of triangular wedge that would be blocked off in here if we were to add in, say, y equals 0. Right? So that kind of blocks the view there, but you can see there's that shape, that's that little triangular block in there. All right? So that's what we need to integrate. So what we want to integrate then, we need to switch out of x being first. So, we can switch to something else. Maybe we can try integrating with respect to y or z first. So any suggestions on which to do first? But, this cursor's like way not where it's supposed to be. So this is the x direction right here. The y direction, the one back there, and z is the up and down here. So one thing we can do is we can try and just set up, see what it looks like if we do, pick one of them and just see what happens. Oops. So let's go ahead and do that. Let me swap back over here. All right, so let's say we do y first. Right? Then y, if we remember that shape, y is going to start back here on the xz plane. So it's going to start at 0, and it's going to go all the way up to this plane y equals z. And it's going to go all the way until it hits that. Sorry, y equals x. So the upper bound here is x. Right? So now, if we integrate the x out of it, what we get left, the shadow of the shape, is this purple-green triangle I have right here, actually. So it'll look something like x, z. Let's say here's, our fourth root of pi. That was, I don't know what that was. Right? And then it'll be this shape. Right? And now that we have this, we can say, well, what do we need to do? Oh, sorry, we integrated y first. And now we can try and see, well, can I integrate x yet? Can I integrate y? Or do I need to integrate z? So if you want, what you can do is compute this integral with respect to y first. So it's going to be 4y cubed. So you're going to have 4x cubed z cubed sine x to the fourth. These are going to be what's left over. And if we look at that integrand, we can actually compute this integral now with respect to x. So at this point, the order doesn't matter. Right? Sorry, this line right here I should emphasize is z equals x. So why not? Let's go ahead and knock out x next, and then we'll do z. So if we do the x integral next, x is going to go from 0 to z here. And then z will be its same self. All right. So we should be able to do this without any problem. Let's see. Oh, wait a minute. Actually, there is a problem with doing that. So if we integrate this with respect to x, okay, either way, we're going to wind up with that. Never mind, it's fine. All right, so let's go ahead and integrate this as it is. Sorry, I was thinking about something. We're going to be stuck with this anyway. All right, so let's integrate this. I have 0, fourth root of pi. All right, when you integrate this, it's actually just going to be negative z cubed cosine of x to the fourth from 0 to z, dz. Okay. And so let's finish this off here. So we plug in the z. Oh no, what was I thinking? I don't know what I was thinking. This is fine. All right, so let's plug this stuff in. 0, fourth root of x, or of pi. Plug in z, so we get negative z cubed, cosine of z to the fourth. Plug in 0, cosine of 0 is 1, so this is just going to be plus z to the third, dz. All right. And now we can compute this integral. So, oops. All right, so integrate this. This part is going to give us negative 1/4 sine of z to the fourth. Right, that's just a u substitution, just like the one we did up here for x. Here, this is 1/4 z to the fourth. And that's from 0 to the fourth root of pi. All right. And now just plug in all our stuff. So plug in the fourth root of pi. We're going to have 1/4. This is going to be sine of pi, because we're taking the fourth power of the fourth root, plus 1/4 pi. Right? That's plugging in the top and the bottom. Sine of 0 is 0. 0 to the fourth is 0. Now sine of 0, or sine of pi is just 0, so that's gone. So all we have is just a pi over 4. That's it. Yeah, sorry about that earlier. I was thinking we are going to get something like x to the fourth cosine x to the fourth or something at some point. But even if we did, we could still do that with integration by parts. Yeah, here. Right. So it all comes down to, it really does come down to sometimes just trial and error, right? Like we know we can't do x first. So, put something else first and see if it works out. Right? If it doesn't work out, we can always try something else. Right? So it's sort of completely up to you what you want to try. But yeah, at the end of the day, just, we know x can't be first, switch it somewhere else and then see where it goes from there. All right. So that's it for this session. And this is why I only put 4 problems, because sometimes they can get a little interesting. All right. Well, if there's any questions, let me know. Otherwise, that'll be it for today. I gotta go fix a video on WebAssign, it appears. All right. Cool. Well, take care, and I will see you next time. All right. Let's go ahead and do the math problem. All right. Where'd my pen go? Pull this up over here. All right, so I only have 4 problems today. And it'll be sort of enough to get the idea, I think. So problem 1 here is just, straightforward compute an integral. No tricks, no surprises, anything like that here. So I don't know if you've tried it yet, but go ahead and try this integral on your own real quick and see how it goes. And then we'll work through it here. I did fix this lecture video, the second video in the April 7th lecture. I don't know what happened there. Somehow a letter got left off the end of the link. Maybe it looked too much like the @ sign or something. Okay, let's go ahead and compute this one. So if we do the integral with respect to z, the x and y don't do anything, and it's basically xy squared times 1 over z. So you integrate that and you get ln absolute value of z. We're evaluating this from 1 to e, dx dy. Minus 2 to 2, minus 1 to 2. Let's plug in this stuff and see what we get. If we plug in e here, we get ln of e, which is 1. So we get xy squared. And then minus, we plug in 1 here for z, we get ln of 1, which is 0. So all we have is just xy squared. Then dx dy. Right, now it's a straightforward double integral. Right, so just integrate that. With respect to x, we get 1/2 x squared y squared from 1 to 2. Right, so plug that stuff in. This is going to be 2y squared. Plug in the 1 minus 1/2 y squared dy. So we're integrating from minus 2 to 2, 3/2 y squared dy. And, well, integrate that, we get 1/2 y cubed from minus 2 to 2, which is going to be 8. Yes, 8. Pretty sure that's right. Okay. So, any questions at all with this one? Hopefully this was just straightforward, do the computation, no big deal. All right, awesome. Okay, so let's look at problem 2. Right, so problem 2 is we want to find the volume of a region of this prism in the first octant bounded by the planes. So let's write this down. First octant. Remember, the first octant is where x, y, and z are all positive. Right? So it's bounded by that. The plane y equals 4 minus 2x, and z equals 6. Alright, so we're looking for something in the first octant bounded by these two planes. Okay, so let's try and make a sketch of what's going on there. So I'm going to draw the first octant. Here we have x, z, and y. All right. Now, with that, we need to draw all this stuff. So let's say 3, 4, 5, 6. Let's say there's z equals 6. There's 4 there, and add a 4 as well. All right. So to graph this thing, we talked about graphing sort of planes and cylinders and stuff like that way back in the semester. But just a reminder, so like to graph this thing here, this plane y equals 4 minus 2x, since there's no z variable in that, what we're essentially going to do is draw this line in the xy plane and then just extend it parallel to the z-axis, because that's how it's going to trace out its shape. And it's just going to go straight up and down, and it's going to be parallel to the z-axis. So if we graph this line, it starts up here at 4, it ends down here at x equals 2, and it's sort of just this piece right here. Now the plane part of it, extends all the way up. And here we're only interested in the first quadrant, so we only need to worry about the upward part of it anyway. So how do we kind of cut this off? Well, we can look at what the plane z equals 6 is doing. The plane z equals 6 is going to hit this value right here, and it's going to be parallel to the xy plane, so parallel to this floor. So let's look at the way it intersects the yz plane is just a horizontal line. Okay. And the way it intersects the xz plane is another horizontal line. When we draw this line here, though, for the intersection with the xz plane, we want to make sure it's parallel to the x-axis, right? Because it's going to intersect the xz plane in a line parallel to the x-axis. So we sort of want to, from this point, draw a line with that same slope. So hopefully I can accomplish that. Right, so something like this. This is how it's intersecting the planes. The YZ plane and the XZ plane. All right. So now to see what this plane is going to do, we know this y equals 4 minus 2x. It's going to be parallel to the z-axis, so it's going to be vertical in the YZ plane and vertical in the XZ plane. So we can just draw a line straight up here. And that's where it's going to intersect the plane z equals 6. And now we can just connect it. And hopefully you can kind of see our shape now. So this blue square, or blue rectangle here, is sort of the front of this. Right. This is the top, this triangle. The bottom, maybe I'll use dotted lines here to say this is the back side of the shape. So it kind of looks like if you had like a rectangular block and you sawed it in half along the diagonal there, right, along this line. So you should have kind of like a triangular prism there. Does that hopefully make sense? If I add these in, the shape will look a bit better. That hopefully makes some kind of sense there. what we're looking at. Now, these other edges back here, like the bottom of this is z equals 0. The back side of this is x equals 0. And sort of the left side of this is y equals 0. Right? And those are just the 3 coordinate planes. Right? And we get those because it's stuck in the first octant, so those form parts of the boundary as well. Right? Hopefully that kind of makes sense there. Right. So now that we have that settled, it's just a matter of, let's actually get the integral set up for this. Right. So we're calling this region here D. So for a triple integral, the volume of a region is given as the triple integral over D of dV. Right, that's all there is to it. Just like we could use a double integral to compute area by integrating over a region and integrating just dA. For volume, we can do a triple integral over the solid region of dV. Same thing. Sorry. Same idea. Okay, so now that we have that, let's try and set up some bounds here. So the order doesn't particularly matter in this problem. But I mean, once we pick an order, we can't really change it. But this problem should be able to be done in any order without any issue. So, any suggestions for, for a variable to integrate with respect to first? Well, an order to integrate in. What's first, second, and third? Anything is fine. More left in that cup than I thought. All right. Y, X, Z. Sounds good. Okay. So let's go ahead and set that up. So if we want to integrate in the Y direction here, we want to start... We always start from sort of the most negative side on an axis and go to the positive side. So here, in this picture, Y goes from left to right, X goes from back to front, Z goes from bottom to top. Now that left, right, back, front, bottom, top stuff, that's going to depend on if you rotate your graph and have your axes in a different order, then you're going to get a different picture. Or, which one's which is different. But, the key thing to remember is you always go from smaller values to bigger values. So if we're starting with Y, here we're looking at the left edge and we're going to the right side. Right? So the left edge here is this back wall here, the XZ plane, which is Y equals 0. And actually, Y is probably the best choice here, because it's already set up for us to do this with Y first. Because as we move to the right, sort of no matter where we start on this back wall, if we keep walking parallel to the Y-axis, the thing we're going to hit is this blue plane right here every time. So that means the upper bound for Y is going to be 4 minus 2x. So this is why it's better, at least it's better to integrate Y before X in this situation, because that's already set up for us. Now, if you wanted to integrate X first, you would still be fine. You could start on this wall over here, X equals 0, and then you would just have to solve this for X. if you wanted to integrate x before y. So it's still very doable, but integrating y first is the best option here. So now with triple integrals, setting up these later two integrals, the bounds on this, setting that up to figure out what region we should integrate over, how to set up these bounds. You can do it from the 3D picture, but I think that tends to look pretty confusing sometimes. So what we need to do, because what we're integrating over for these two is the shadow of this shape in the XY plane. Or sorry, in this case, the XZ plane. Right, so we want to basically take this shape right here and squish it into the XZ plane and see what happens. And if you look at what's going to happen when we do that, we get something pretty simple. So let's say here is 6, here's x equals 2. The shadow of this in the XZ plane, so against this sidewall here, when we squish that down, all we're going to get is this rectangle right here. That's all we get. Right, so this slanted edge is sort of gone. And so that makes the bounds on this pretty easy to do, right? So x only is from 0 to 2, z is from 0 to 6, because this is just a rectangle. Right. So again, just like with all the double integrals, this is by far the most important part, is setting up the bounds, more than anything else. So we'll compute this, but want to make sure. Any questions at this point? Awesome. All right, so let's go ahead and do this computation here. So 0 to 6, 0 to 2, integrate this, and we're just going to get 4 minus 2x dx dz. All right, integrate this with respect to x, and we're going to get 4x minus x squared. This is from 0 to 2, easy. So that is 4 dz. And so that works out to be 24. Right, so not all that much going on here in the computation part. Again, by far the most interesting part of this problem, and really sort of the multivariable calculus part of this problem, is doing that integral. Or sorry, is setting up that integral. Sorry. Any questions here? All right. Excellent. So let's look now at problem 3, which is a bit more interesting. Right? So here, we want to find the volume of a solid where D is bounded by the paraboloids y equals x squared plus 3z squared plus 1, and y equals 5 minus 3x squared minus z squared. Right? So we want to look at the region bounded by these two shapes. Right? So the fact that the y is the variable that doesn't have the square here means that these paraboloids, those kind of bowl-shaped things, these are going to open along the y-axis. One of them's going to open to the left, to the right, one of them to the left. I keep thinking I have to mirror my hands for the camera. Then I remember I flipped it. All right. So let's look at what this shape looks like, because if I try to draw this, it's going to be a catastrophe. Let's see. Oh, I think I already have this one here. So this is the shape we get right here. So the orange one here is the orange one here is going to be, where's my cursor? Because it's never in the spot it's supposed to be. There we go. This one here, this is x squared plus 3z squared plus 1. And the blue one here, this is 5 minus 3x squared minus z squared. Right? Let me see if I can. Okay, good. Maybe you can see a little bit better what's going on here now. So you sort of have one bowl going to the right, one bowl going to the left, and it kind of it closes off this like capsule shaped thing. Right? So you can see the left edge is on the orange piece here, and the right edge of that shape is the blue piece here. Right? Hopefully you can kind of see how these two things are cutting each other off. It's sort of like imagine if you take like a small cup and a slightly bigger cup and stick one inside the other. Stick the opening of one in the opening of the other. It's going to cut off some kind of shape. It's something like that. It's a little bit different than exactly that, but it's kind of that idea. Right? So hopefully this makes some sort of sense, what this is. Encourage you to try plotting these two yourself. So you just, plot the two equations using a contour plot, since you're trying to graph equations. And yeah. All right, so hopefully that makes some kind of sense. So when we want to set up the volume for this, the integral for the volume is going to be a triple integral, again, over d of dv. And we need to decide on an order of integration. Yeah. So here, there's really only one variable you'd want to put first that's not going to be horrible, and that's y. The reason you want to do that is here, well, if you remember what our shape looked like, the left edge is always the orange paraboloid, the right edge is always the blue paraboloid. All right, so since it's most simply described like that, you want to make those your bounds. But also, you want to do it because if you tried to do any other variable, this would break into like 3 or more pieces, which you probably don't want to do. All right. So here, sorry. Remember this, the orange one was first. So this is the orange one. This one was the blue one. So that means this one's on the bottom. And the blue one was on top. Right. So now the question becomes, well, do you integrate with respect to x or z next? Well, to answer that question, you really want to sort of look at, well, what is the shadow of this shape, in the XY plane. So if we come back here, the XY plane is back here. Or sorry, XZ plane, I mean. It's back here. So if we look at it sort of dead on like this, what's sort of the shadow of this shape back here? And it's kind of hard to tell from in here, I think. It's not so easy to pick out graphically what this shadow ought to be. So we can do it analytically. The way we can do it is say, well, where is this shape sort of the widest at? Where it's the widest at is going to dictate what the shadow looks like. Well, it's the widest when these two things are intersecting. That's as far out as it goes. So let's find out where the intersection is. We know both of these are y equals, so we're just going to plug one into the other. Right? So let's say plug this one into the second one. We get x squared plus 3z squared plus 1. This has to equal 5 minus 3x squared minus z squared. Right? And we did something similar to this. What problem did we do yesterday? Was it yesterday? I think it was yesterday. We did some kind of volume problem. And we did something similar. We found the intersection of two graphs. I think we ended up solving for z first and then using that to figure out what x and y had to be. Anyway, so let's move all the variables to one side and all the constants to the other. So I'll put the variables on the left. So moving this over, we're going to get 4x squared plus 4z squared equals 4. Okay. And so this says this is x squared plus z squared equals 1. So it turns out what we're integrating over for the last two bounds is actually a disk of radius 1. Okay, so we're really integrating over all right. We're really integrating over something like this. Right. So now we can use that to finish setting up the bounds. So I know I'm integrating over a circle here. So as it'll turn out, the order you integrate this in really doesn't matter. So let's say we do x then z. Actually, let's do z then. It doesn't. We'll do x and z. So if we do x first, we start on the left side and go to the right side. The left side of this is negative, or x equals negative 1 minus z squared. The right side is x equals square root 1 minus z squared. So negative 1 minus z squared, square root 1 minus z squared. And then the z values, down here is negative 1, up here is 1. So minus 1 to 1. Right. So that would be, at least in set up in Cartesian coordinates, this is how we would integrate this. So let's actually do this integral. Right? This looks like a hot mess here, but it's fine. Let's integrate this. So I'm going to copy this. We actually have room to work on it. Right, so I want to integrate this. Now I can integrate this with respect to y, no problem at all. Shade in this disk here. So I can integrate this with respect to y, no issue. And all that's going to happen when I do that is I just do top minus bottom. Right, because I integrate 1 and I'm just going to get y. So this is going to end up being this minus this, which is 4 minus 4x squared minus 4z squared. Right? I'll let you, if you're not sure about that, right, just compute this as you normally would, and you'll see you just end up doing this minus this. Now, if we look at this integral here that we have left over, right, this double integral we have left over, we could try and compute this, and, well, you know, we'll get something that we could do. It is possible to do, but it might not be fun. So any suggestions on what we could do to this integral right here to make it nicer to compute? Other than throwing it into Mathematica, of course. Hint I'll give is think about the region of integration for this problem. Think about what that shape is, and if there's anything that sort of would go well for this. So we did these yesterday. This is a circular region here. Now, this isn't your usual x and y, but why not say, I don't know, x is r cosine theta? Yeah, we want to use polar, where instead of y, we just have z, but it's the same thing. Right, so we can switch this to polar. This region is a nice polar region. So it's going to be a nice 0 to 2 pi, 0 to 1. This stuff in here, right, we're going to have x squared plus z squared equals r squared here. So inside here, this is just 4 minus 4r squared times r dr d theta. Right, so just because it's not exactly x and y, it doesn't matter. We're looking just at this region in the xz plane. It's a nice disk. Disks work better with polar coordinates. Right, now we just have to integrate this, which, if you think about it, it's probably a lot nicer than what you're going to get out of this one. All right. So let's see, we integrate this with respect to r. And that's going to be, let's see, 4r, so 2r squared minus r to the 4th from 0 to 1 theta. So that's 0 to 2 pi d theta. This is just going to be 2 pi at the end of the day. So, you know, polar coordinates are quite a powerful thing to be able to use. Right? So if you kind of think of what just happened here, we've basically done an integral by sort of combining a Cartesian direction with polar coordinates. So that's a little bit of a hint for what we'll talk about on Friday, actually. And it's the lecture videos. I think it's the April 8th lecture videos. But yeah, they're pretty interesting stuff there. All right. So, any questions before we move on to the last problem about this one? All right. So the last problem is just a, hey, here's a problem, or here's an integral, compute it. So problem 4. So here, we just want to evaluate, let's see, 0 to the 4th root of pi, 0 to z, y to z of 12 y squared z cubed sine x to the 4th dx dy dz. All right. So if we look at this thing here and we try and compute it, we see that, all right, well, we need to somehow compute the integral of, this is sine of x to the 4th, just to make sure here. We need to somehow compute this. Well, that's a little bit of a problem because we can't compute the integral of sine of x to the 4th. There's no u substitution, there's no integration by parts, there's no trick that's going to get us through that. So much like with double integrals, the answer is going to be, well, switch the order of integration and see if something else works out. There's some kid outside who's not very happy. All right. So, to do that, we're going to do the same thing as last time. We need to be able to figure out, well, what is this region we're integrating over? So, these are the bounds for z, for y, and for x, respectively. So let's write those down. Y and x. So these are our bounds for x, y, and z. Now let's see if we can kind of sketch what's going on here. So we want to try and sketch this, or at least make an attempt. I will say I'm very, very bad at sketching more than one plane at a time, so this is going to be a best I can do picture. So here, y and z are both greater than 0, which means that x also has to be greater than 0, so all of this is going on in the first quadrant again. Which is always nice. Right. So here, from this bound, or let's just mark up here, let's say this is the 4th root of pi up here for z. All right, let's see here. I want to graph x equals y. X equals y is going to look something like this, right? At least in the xy plane, it's going to look like that. So if we, do I want to do this? All right, let's do it. Let's see what happens. So the whole plane looks something like this. Something like that. Hopefully this doesn't get too terrible. Right. So that's that plane. Now let's look at the plane that's we're going to get from x equals z, the other bound. So x equals z is a line that looks something like this. I should make that a bit shallower. Right, it looks something like this. So let's see here. This one's hard to draw. Right, let me maybe change the line a bit. Yeah, this is hard for me to draw. Right, so they're going to intersect on some line right here. Right. So I'm going to show you this in Mathematica in a second here. But you get this kind of like pyramid looking shape that's sort of enclosed back here by the XZ plane and these three pieces here. The green triangle, that blue one, and this red one. So because my skills of an artist are not really that great there, let me show you this in Mathematica. So I'm going to show it first from the same perspective where z is going up, x is coming at you, y is kind of going to the left. So it sort of looks like this. These are the 4 planes in question. So this blue one here, this is x equals z. This orange one here, it's kind of a dark orange here, but this is x equals y. This green one is z equals the 4th root of pi. And this red one back here, this is the xz plane itself. So if you look at it, I don't know if my drawing looks anything like this at all, but let's even temporarily take out the xz plane. Right, so if you look at it, we have sort of this little pocket in here, this little like quarter of a pyramid looking thing right here. Right, that's the volume that we're finding. That's the region that we're integrating over. Sorry, is that little piece in there. So if we add that back in, you can see like these black lines right here and here. Those lines kind of cut off shape. Right? And you can see it kind of getting cut off over there as well. Right? I don't know, for me personally, regions that are kind of cut off by a whole bunch of planes are always really hard to visualize. But does that seem to make some kind of sense what the shape we're integrating over is here? Might even be a little better to try and cut all these off at that value. That looks any better, but there's a solid bounded by all these pieces. So we want to try and integrate over this region. All right, so let's swap back over here. Now, we know we can't integrate x first. So we have to integrate anything other than x first. Oops. There might be one of them that's better to do than the other. But in some sense, you know, it might just come down to a bit of just experimentation. right? To figure out which variable to integrate with respect to first. So let's do this. Any suggestion for what variable to integrate with respect to first here? Y or Z? Should be able to do either one of them. Right. So let's do this. Let's integrate with respect to y first, and let's leave the other two off for now and see, like, after we do that first integral with respect to y, do we get something we can handle? Right. So if we look at this shape, might be still a little hard to tell, but this red plane here, it kind of moves parallel to y, so it's never going to come into the bounds, at least in my hand drawing here. So the back of y sits on the xz plane, so the lower bound is 0, and y goes forward all the way until it hits this x equals y plane here, so it's just got to be x. So y is only going to go from 0 to x. Right? And I'll pull this back up in Mathematica real quick. So this direction is the y direction, the one that moves from here to here. So the backside of y is this. This is the xz plane. This blue plane here moves parallel to y, so it's never going to be an issue. And so y ends on this plane right here, this orange-yellow one, which is x equals y. So that's why the bounds for y simply go from 0 to x. Right. So let's do this integral with respect to x and see what happens. Right, so integrate with respect to y. If we integrate this with respect to y, you're going to get 4y cubed z cubed sine of x to the 4th. So let me just note that here. So we're going to have this stuff from 0 to x. And so when we plug this in, we're going to get 4x cubed z cubed sine of x to the 4th. That's going to be the result of doing that y integral. So at this point, can we integrate this with respect to, or does it matter what order we integrate with respect, or yeah, what order we integrate in? Either x or z first. So what we might want to do is try and figure out the shadow in the xz plane of this. Right, since we integrated y first, right, if we go back to Mathematica for a second, so we're trying to sort of look at, well, what's this shadow here? And the shadow's cut off by the green plane up here and this blue plane here. Actually, maybe it's better to see it from this side. It's really... So this here is the bottom edge. Nope. There we go. This here is the bottom edge, this diagonal line. Hopefully you can kind of see that in there. This is the top, and this is the side. So we get this like upper right triangle here. Right? So that shape, this. So this is the 4th root of pi. This line here is z equals x, and we're trying to integrate over this. Oops. Switch back here. Yeah, so we're looking at integrating over this region here. And now we have to decide, well, do I want to integrate x or z next? And really, you can just sort of pick one and see how it goes, right? Like there's no harm at all in doing that. So let's do that. Let's just pick one and go for it. If I look at this region I have here, it's a little bit simpler to do x first because x starts at 0, whereas z starts at x. So let's try doing x next, and we'll do x and then z. If we do x, z, x is going to go from 0 to z. Z is going to go from 0 to 4th root of pi. Right. So to integrate this, we're just looking at a u substitution. So I'll leave the u substitution to you, but the u is going to be x to the 4th. So what we're going to wind up with is negative z cubed cosine of x to the 4th. That's going to be the integral of this from 0 to z. All right, so if we plug that stuff in, this is going to be minus z cubed cosine of z to the 4th plus z cubed, right? Because if we plug in 0 here, cosine of 0 is 1. All right, so now we're integrating that. If we perform this integral, this is going to leave us with minus 1/4 sine of z to the 4th plus 1/4 z to the 4th. And this stuff is getting evaluated from 0 to 4th root of pi. And so just plug this stuff in. This is minus 1/4 sine. Plug this in, it's going to just be sine of pi plus 1/4 times pi minus negative 1/4 sine of 0 plus 0. And sine of 0 is 0. Sine of pi is 0, so those are all gone. And all we have left is pi over 4. Right. And that's that. So it worked out to do x next. We just couldn't do x first. So it could happen that, say, we tried to do x as the second integral and it didn't work out. So you just swap it to the third one, right? It does, it can become trial and error sometimes to figure out, what's the right order to do this in. But, right, so any questions before we end for today? Oh, thank you. All right. Well, with that, I'll see you on Friday for some cylindrical and spherical coordinates. So take care, have a good afternoon, have a good Thursday. I'll see you next time.